It's my pleasure to welcome you to the lecture of distributed data management today. And today we will talk about query processing. I mean, query processing is at the heart of data management, right? Whether the data is stored in a central space or whether it's distributed. We talked about distribution of data, partitioning of data in the last time, right? And now we have to figure out how do we deal with data from different areas, from different places, right? And then we will talk a little bit about localization and about response time models. So what we talked about last week was basic architectures for sharing data, for partitioning data, right? And there are basically three major architectures. The first one is a share everything architecture, where the nodes share the main memory. So the computing power, everything that is done with computing is shared between all the nodes, right? And of course, this gives you a central point of failure, right? A central point of a central bottleneck, if you want it like that. On the other hand, you can ship data from different locations into that central processing area and then simply work on it. Then there's the shared disk architecture, where you usually have a storage area network, and all the data resides on that storage, on that logical storage device, right? And you just share the disk, basically, right? The problem is, well, this is very often done like that, right? So that you don't have to care which disk the data actually comes from, and that you can shift data around. But if you need it at a central point, you simply get it. And then you have the share nothing architecture, and in the shared nothing architecture, like the name shows, neither the disk space nor the computing facility is shared, but the data has to be shipped to the computing facilities, and there are different computing facilities dealing with the same or different data at the same time, yet in different locations, right? And you see that from the share everything architecture, where a central control is very easy to establish, over the shared disk architecture, where you can compute in different areas, yet all the data comes from one place, so the communication is kind of limited, to the share nothing architecture, where everything is distributed. The data has to be shipped to the processors. The processing units can work in parallel. So this is a very powerful model. However, it is a very complex model. It's a model that needs a lot of synchronization if you want the model or if you want those results that you would expect to have, right? So think about a workflow or a program that does something in a certain way, and now you parallelize it, right? Then you need to figure out which parts are ready, which parts are not ready, and at some point synchronize them. And this is much more, much more difficult. However, this is kind of the reality that we have today, right? Everybody has a PC on his desk, and those are not stupid terminals anymore, stupid clients anymore, but they're full-fledged computers, right? And even if you think about your mobile phones are better processing units, better computing units than what we had 20 years ago as desktop computers, right? So it's kind of growing, this idea of distribution, this idea of distributing both the disk space where the data is actually stored and the computing power, where the data is actually processed, right? And of course, this is the biggest communication problem. On the other hand, it's very elastic, it's very scalable, because you can just add in new devices. A new mobile phone gets into the cell, you get more computing power, right? And you get a place where to store something. Okay, we talked about data being distributed across different nodes, and there are two concepts. One is the fragmentation, right? How do you fragment your data? Do you do vertical partitioning? Do you do horizontal partitioning? Is data from different semantical meanings at different points, right? So, for example, if you have a company, then the different departments might store the data that is valuable to them within their department. However, you have some company-centric view combining all the data, right? Or you could fragment by years, right? Data from last year, data from the current year, data from 10 years ago. And then fragment it like that. And then you have the question of allocation. So where do you put your data, right? So talking about storing data year by year or from different years, it would allow something like archival, right? So the data that is this year's data is probably data that I need very often, that I need to update, that I need to work with, that I need to draw conclusions from or use for decision support. Last year's data is maybe less interesting, so can be stored on slower disks or even offline. Data from 10 years ago may be interesting for, I don't know, tax deductions or, you know, like complex stuff that you need once a year. But you know, like it does not have to be at the heart of your system. The second thing with respect to allocation is the question of replication, right? So in large system, you want a certain degree of resilience against failures, right? You want your system to be robust, even if a node drops out of the system. So, I don't know, either one of your company's branches burns out, or the hardware fails, or whatever happens, right? The network is down, so you can't reach a certain location. You still want to have access on the data, right? So the question of where do you allocate chunks of data that are actually the same data, that are redundantly stored, is a question that caters for robustness in your system. So interesting questions, and behind all these questions is always an optimization problem, right? Usually a knapsack problem that really depends on the application that you're going to do, right? So how much replication do you need? How much fault tolerance do you need? How much availability do you need? How much parallelism do you need, right? So if you're computing heavy, parallelism seems a very good idea. If you have very small computations, then why caring about parallelism, right? On the other hand, availability, so if you have nodes dropping out very often, for example, you do what I just said, right? You're using mobile phones in a network cell for data storage or data processing, or I don't know, Bitcoin mining or whatnot, right? Then you have roaming behavior, you have people dropping out of the cell, you have people just shutting off their mobile phone or so on, right? And you have to deal with that, so you need a stronger robustness. And depending on what you need, you have to make certain design decisions, right? This is what I'm saying, right? And there are many possibilities and many decisions that have to be taken. Good. With this in mind, we enter the first detour today, and I want to talk or Jose wants to talk a little bit about classical query processing like we had in databases, right?
Yeah. There you go. Okay, so yes, at its core, what we mean by query processing, where that query processing is all about answering queries. So for instance, if you just ask how many students we have at the university back in 2016, you will get an answer like the one that I'm showing in this slide. But this is just the view of what the user expects from a database management system. But inside, what we do care about is about additional constraints that we must satisfy in order to have a system that is actually doing a good job in answering queries. So for instance, we care a lot about response times. We don't want the user to be waiting to get an answer for the query. We care about having the possibility to be able to answer many queries simultaneously. And we care about the efficient use of the hardware that we have, and several other things actually. And all of these things are the major topic of relational databases too, offered by our institute as well. So what I'm going to do for the next following slides is to give you a summary on how do we do it when we don't have a distributed environment, just to give you what is behind this query processing optimization problem. And then we will go to what are the differences when you have a distributed environment. So it's a brief summary. I mean, there's a whole lecture on this topic, so I just wanted to point that out. Okay. So in general, this is what we have when there's no distributed environment. You just want to do query optimization, and you start right here with the query. And usually, what you have is some sort of a declarative language, such as SQL. And the first thing that you do is you have a parser that takes whatever you type in and rewrites, or I think the best way to say is translates the query to a naive query plan. It is naive because it is just a simple mapping from SQL to some sort of relational algebra, actually. And then what we do is query rewriting. So this is a step that is very similar to what we did when we were doing algebra in elementary school. Then you have to simplify the expressions, you have to eliminate redundancy. This is what is happening very quickly in the query rewriting step. Then you have a query plan, but it's not the best query plan. So what you need is to do optimization. And this is done in two steps, very often actually together. So we do an optimization of the query plan looking at the context of the system. This thing that we have here, the metadata catalog. So now that we have some sort of a representation in relational algebra, what we want to do is to consider what indexes do we have, what kinds of data are we dealing with, and this is actually at the core of the query optimizer. And at the same time, what we want to do is to, given that we have several operators now in relational algebra, we offer different implementations for that. And this is what we do in the physical optimizer. This is what we want to do. We want to take into consideration, given certain constraints, what exactly of implementation of which operator we're going to take to finally deliver the query plan to be executed. We will go into the details of every step now. So the first one, we have the query, then we have a parser, take the query to some sort of form SQL, and then we go to a naive query plan. What is important to notice here is that what we want to do is to build a tree when we have at the nodes the operators that we need in relational algebra. Because now the main difference is, let me give you an example to see that. So if we have a database very similar to the one that we used last week, we have a table creature, table hero. Table creature has an ID for the creatures, name and type. For the hero, you have an ID as well and the name. And then we record in the fights table the fights between creatures and heroes. So we have this idea of orange keys going from creature to fights and going from hero to fights, and the location and the duration of the fight as well. Now, as an example that uses this database, just to give you an idea of what is happening from the first step. So we have an information eaten away, a query. We have a query, and we want to express the query in SQL. So the query is just give me the names of all the creatures which fought at the gates of Acheron. And using this simple database, this should be at least one possibility of doing an SQL query on that database. So basically, we're just saying what do we actually need is the creatures table, the fights table, and we need to make sure that the location, which is given by the query, fits exactly that description, and we need to make sure that the ID of the creature is the same ID that we're using from the fights table. This is just one possibility to do a simple SQL query given that database. This is the input that we have, and then what we do is we take our parser, and the parser basically very quickly just takes exactly as it is the SQL statement and translate it to a simple relational algebra. So we have clearly from this query a Cartesian product between creature and fights, and then we have a selection that goes into the specific conditions that we have. We abbreviated gate of Acheron here as go A with an AND condition that matches the right tuples in the two tables. And then we just do a projection on the name. This is a simple translation. So why do we do that? From the declarative language, we have no idea what specific operators do we need to actually perform the query. And this is the first step. We need to know what kinds of operations are behind the query. And this is what we get by doing this translation. By having a relational algebra representation, now we know that we need a Cartesian product, we know that we need a selection, and we know that we need at the end a projection to actually answer the query. This is the first step. But we are not over yet. Usually you have some sort of a tree representing what is happening, and this is what we have in this slide. So basically we have at the bottom the two tables, the two relations that we are using, creatures and fights. Then we have the operator, the Cartesian product. Then the selection on the conditions that we already mentioned, and at the end the projection. So this is what we have, but we are not finished yet because there are some things that we need to improve to make this query a better query to be answered by the system. And as I said at the beginning, the second step is just doing what we did when we were doing algebra, but doing it with relational algebra. What we want to do is basically perform certain things that independently of what the system state is actually work. And people have found that if you have a relational algebra, you can eliminate some redundant predicates that always makes, that turns out in better performance issues when you do the queries. You simplify some expressions. You do some sort of normalization, basically meaning you take the disjunctive normal form from the conditions that you have, and so on. And I said, we do this regardless of what the system state is. And what do we mean by the system state? So the system state takes into consideration what we actually have. So the size of the tables, the indexes that we have, and this is actually right here in the metadata catalog. Regardless of that, the first thing that we do is just simplification, redundancy, go normalization very, very quickly. We have this system state, but we don't use it, not yet. This is part of what we do in the next step, which is when most of the time the query optimizer is actually doing a great job, because there are many things that we can do to improve our query for the execution plan. Basically, there are two types of optimization here. We have algebra optimization and physical optimization. Both of them now are using the system state. So in the case of algebra optimization, we have different approaches to do it. We have, for instance, some heuristics that we can apply that people have found to actually do a big difference when we want to do queries. Then we have some models, cost-based models that we do based on the system state. We will do that in the following slides. And most often people are trying to use some sort of statistics from the data to actually incorporate in the cost models as well. But at the end, what we have in the algebraic optimization is just a relational algebra expression. So we have still no idea on how to execute the query. So the next step is to do this physical optimization. So for every operator, we offer different ways to execute the operators. For joins, there are many ways to do joins. Selections as well, how do we do the selections physically? And this is the decisions that are made in the physical optimizations. We will go into the details as well. What we mean by heuristics optimization is we just take what we get from the relational algebra expression, and we just want to make sure that maybe we still don't have the optimal plan, but what we do want to do is to really get rid of those plans that we know that will be really bad. This is what we want to do. And people have learned some basic heuristics. We show here 3 of them. Basically, when you have selections and they are with complicated criteria, you just try to split them into multiple parts. This is something that actually works. Secondly, what you want to do is, so you know that certain operators are actually more expensive to perform than certain other operators. So what you want to do is to execute as early as possible those that are cheaper. And these are selections and projections. These are very easy to do. And at the end, what we want to do as well is to force joins. That means that whenever you see in the relational algebra expression that you have a Cartesian product that follows a selection, this is actually a join. And it's much more efficient to do joining than doing the Cartesian product. So these are the heuristics that people have learned that actually make a difference to have a very nice execution plan for the query. So if we do that for our running example, this is basically what we have now. So we do push the selections and projections first. So we do the selection over here. We do the projection over here. And we know that we don't need all the attributes from the table. So we just project what we actually need. We need the ID of the creatures and the names of the creatures because we want that at the end as an answer to the query, and here as well. And what is important to notice from here is that now we don't have any more the Cartesian product. This is one of the things that we do. We force the join to substitute what you have at the beginning. Yeah. So we have now a join that we will offer different options to do it better than doing the naive Cartesian product. Okay. We're not done yet. So what happens here is once we have applied these heuristics, there's still more room for improvement. And what people have found is that they can actually now take a look at what the system looks like in terms of the tables, the size of the tables, the indexes that you have, and then considering this, you want to optimize the representation of the query. And one thing that you do is a very difficult problem, which is looking at the join order optimization. This is something that we actually care a lot when you do these cost models. And the way that in general these cost models work is they try to enumerate all the possible query plans that exist, that might exist, and then they pick the best one. Given that we don't have too much time to actually do it like that, so what they actually have found to be very useful is using dynamic programming techniques to actually come up with this. And what is basically happening here is that we're relying on a technique that is taking a complicated problem, splitting it into sub-problems, solving the sub-problems, and storing the solutions to those problems. So the next time that you see that problem, you just look it up and take it as the solution to the problem. This has actually been the thing that people have used very often to rely on these cost-based models for optimization. And as I said a few minutes ago, at the end, we still have only a relational algebra expression. So the next step is to do physical optimization. Now that we know this is the relational algebra expression that we want to execute, now we need to look at what kinds of joins implementations do we offer in our system. Do we offer block nested loop join, hash joins, merge joins? We need to decide which one might apply better for the query that we have at hand. And for doing that, you need to rely on the system state. Yeah? This is at the core of the physical optimization. You do the same for selection. So we do a scan, or maybe we have an index that we can use to do a very quickly lookup. And these are the tasks that we actually use in physical optimization. At the end, physical optimization boils down to answer one simple question. So among all the algorithms that we have to execute the different operators from the relational algebra, which one should we use? Which data, which indexes? We need to decide on that. And secondly, we need to decide if it's possible to use pipeline. And pipeline means if we are doing several queries, we're accumulating results, should we store these results and then use those storage results to continue our query? Or can we just take the output from one operation as an input for the following operation? This is pipeline. Sometimes it's possible to do it, sometimes it's not possible to do it. So one of the decisions at its core in the physical optimization is to decide if it's possible to do it, how do we do it? At the end, it pays a lot of benefit if we do it like that. And since to solve these problems, to make these decisions, people have actually found that they have to do these cost-based models that people actually use as well for the algebraic optimization. So that's why at the beginning I said, well, usually what you have is a cost model that involves the algebraic, the way that you do the joins, and the physical optimization, all of them in one single cost model to make the right decisions. This is what people actually do. Yeah. So for our example, at the end, what we have as an execution plan is the following. We have an index that looks at the fight's location. So this is done very quickly. Then on the table creatures, what we have is just the primary index to get a final join, and we decide to do a nested loop join to finally do the projection. So this is what happens for this example, for this specific example. What I wanted to say with this simple example is, so in general, this idea of doing centralized query processing is an old problem, actually. It's a very well understood problem. If you look it up, you will find even research papers in the 60s, in the 70s, where people were actually trying to do that. It's very well understood, but there are still some open issues. So for instance, the idea of designing more efficient cost models to be able to incorporate not only simple statistics of what you have in your system, but trying to get into this idea of having prediction models behind what is happening in query optimization to let the database do self-tuning. This is actually the topics that today people who are doing this are focusing on. And this is the way that we do it when we do not have any distributed environment. This is the way to go. And if you remember what we did last week in one of the detours, actually this idea of self-tuning in centralized environments is the same that the example that I brought last week with Yahoo are doing in a distributed environment. So they were allowing to see if the system was able to relocate some replicas of the fragments of the database to be able to respond better, just based on simple access patterns. It's the same idea. The system was able to do, in a way, some decisions based on simple rules. And you see that this is just borrowing the same kind of issues from a centralized environment. So this is what we do when we have non-distributed environment. Now the question is, how do we do it when we have a distributed environment? Is the problem different or is the same? What are the challenges? The answer to that question comes now.
So obviously, the problem cannot be all different right now that we distribute the data, but many of the characteristics that we have in the centralized query processing and query optimization needs also to be addressed in the distributed case, right? We have basically the same cost problems. However, we have different constraints because, for example, we now have the network as a component and the latency that the network incurs. So data shipping becomes more expensive, for example, if I ship the data over a network than having it in main memory and being able to work on it, right? So many of the techniques that we've been using, making intermediate results smaller or something like that, right, really count more in the distributed setting than they do in the original setting, right? And the main objective that we saw in classical query processing is minimizing the number of disk accesses, right? So it's always the question, what you're trying to do is disk is slow, reading from disk is slow, computing in the central memory, in the main memory, is very fast. Rather compute 100 operations more than going one time to the disk and read something, right? Because everything you do in main memory is nanoseconds, right? Reading from disk is, well, seconds, tens of seconds, depends on what kind of disk you have, right? And whether you have to move the reading head and so on, right? But far more expensive. More expensive by several orders of magnitudes usually. Good. So the computational time was not a problem in centralized query processing. The number of disk accesses was a problem. Now, if we have distributed query processing on our different architectures, what are our main concerns here? Do we have to minimize the resource consumption, right? I mean, everything is shared, so the computational power is shared, the disk is shared, a lot more concurrency. Do we minimize the total response time, right? I want the results to a query and I want them fast. It does not matter where the data is shipped or how the query is parallelized or not parallelized. It only boils down to how quickly I get my answer, right? Do I want to have maximum throughput? I mean, putting in more and more computing power and more processing units is a good thing, but how does it scale up? If I use the double amount of computing power, do I get half the response times, right? Or can I process double the number of queries with the same quality criteria, right? So these are all questions that are problematic, and this is the design process of query processing. On the other hand, there are some things that are also harder to measure or harder to estimate, because reading from a disk, for example, is quite clear, right? I move the reading head, so-called seek time, I start reading, and then I read sequentially until I reach the end of the data portion that I needed to read, right? Quite easy to see how that works. On the other hand, if I have a distributed setting, I get in much more components, for example, the network. And predicting what is on a network, what is going on the network, depends not only on what I do, what I ship over the network, but also on what other people ship over the network, right? How's the latency of the network? Are there bottlenecks in the network, right? A lot of questions that are very hard to figure out. And everybody has probably experienced some network congestions, right? That just happens. It's like a traffic jam in the street, right? Usually you get to the city center very quickly driving down that street. But if it's congested for some whatever reason, right, can take you half an hour all of a sudden. And how do you predict that? Well, Traffic jams are difficult to predict. Network congestion is also very difficult to predict, right? It has something to do with the throughput, but then there may be accidents, then there may be switches that are misconfigured or whatnot, right? All things that you have influence on, but only so much, only to some degree, right? So the costs that you're using for all these optimization tasks, all that clever things that Jose told you about, right? Or that, oh yes, I will use this join implementation rather than that join implementation, because here I can use a hash index and there I can use a primary index and then it must be faster or whatever, right? Difficult if you don't have the data, if you can't estimate the data, right? And if you have a high variance in costs, then it's guesswork, right? So the basic problem of distributed computing, distributed query processing is it has some more degrees of freedom, right? By getting some more factors into the game and adding a high variance. Both things that we don't like. Higher complexity with more variance. This is something that we don't want, right? We want something that is clear, that is simple, that is easy, right? But the world out there is not clear, simple, and easy. But if I'm talking cloud at the latest, right? You have no idea whether your data is shipped to the US and then computed in, I don't know, Africa, right? And you wouldn't care if it's fast enough. And this is always this kind of, if it's fast enough. So you have additional cost factors, you have additional constraints that you need to figure out. And one is kind of like the network problem, right? Distributed means network. It means shipping data, right? And especially sending and receiving data. Those things that are stress on the physical components, on the computing components. However, also on the entire process. Think about it, you're at a synchronization point, so you need results from different locations, right? And one location is not responding. What do? Basically, you're screwed, right? You wait. And you have no idea, will that come? Is it just a slow network because there's a lot going on? Or has the node died and you should use some other node to do the same calculation that you assigned to that node already, to kind of redo the work and get it from there faster, right? How do you know? You don't. You don't have central control over the whole system, right? So sending and receiving data is a problem. Then you have the problem of localization, right? How do I know where to get the data from? In a centralized system, it's clear there's an index, there's access paths, easy, right? In a distributed systems, data can move between nodes, right? And then there needs to be a ledger, and in this case, usually a distributed ledger, right? That tells you where each data item resides. And when it moves, the ledger has to be updated. And, so you have another indirection that you need. Then problems of replication and caching, right? Is it possible to, you have to introduce some redundancy to cater for a certain robustness in case a node goes down, right? Caching is wonderful. So if some computing unit has the data that you want to work on already in cache, it would be stupid not to use that, but to allocate a new computing unit that then says, right, I need to ship the data first, right? So shipping data is the new disk access in a way, right? So disk access was in the centralized setting the slowest thing possible. Now shipping data is the slowest thing possible. Good. Then you have different network models, you have different response time models, you have structural heterogeneity, right? In the worst case, federated databases that are only loosely coupled and then have to do data integration on the fly because the data is in different formats or in different table forms in the different databases, and you need wrapping and middleware, and oh my gosh, yeah? For query processing, this is hell, right? This is the worst case scenario. You know nothing about your environment. Everything can go wrong in any location, and you at a central point have to decide, right, what to do. What is the best way of doing that? The fastest way of doing that. So you see, it can get difficult. And if you try what Jose told you about, well, maybe join order optimization, let's boil it down with dynamic programming, right? Find the optima and everything will be okay, right? Forget it. Static enumeration optimizations in a distributed setting are not a possibility, are not a choice, right? This is not what you can do. You have more optimization goals, very often conflicting optimization goals, and what is really bad is the limited predictability of costs, right? This high variance. Network delay is something that you can measure at any point in time, but for which prediction is very hard to do, right? And ask Lars Wolf, ask the network guys about this, right? It's still a big problem that people are working on and proposing new measures of quality of service, right? They call it quality of service, and try to figure out how to get the best quality of service of any network, right? Difficult, very difficult. Then you have different cost factors, you have different constraints. Sometimes you have quality of service agreements where you say, but I need this minimum quality of service from you. Then the question is, what happens if the quality of service constraint is broken, right? Are you then kind of, I don't know, stopping the execution and doing something else? Or are you kind of like moving to a different cloud provider or to a different network provider? I don't know, right? It depends what you're trying to do. For some things, these quality of service agreements are very important. For example, if you think Amazon, right, and the shopping facilities, you need a lot of availability and you need responsiveness, right? If I click on something and want to get it into my shopping cart, right, then when I say, okay, let's look at the invoice, right? How much money did I spend yet? What's the worth of my shopping cart? That needs to be updated. And better it is updated in the moment when I put something into my shopping cart and not 5 minutes later. But I thought, oh my gosh, yeah, this is more than I would have expected because the data was old, the data was stale, right? So sometimes there are a lot of optimization goals that have something to do with the business logic. And what we see is that much of the optimization going on in query processing is of a heuristic nature. You try and you fiddle with the thing, right? And then you see whether it performs well or not. And that means it's just optimized on the fly, using some statistics that you have, using some information that you might measure, right? And then you put that into the, for example, the current workload, the current number of users that are concurrently using the system and so on, right? These are important numbers for figuring out which optimization step is more clever or less clever, right? And still the credo that Jose was putting up is valid. You know, maybe we don't need the optimal plan, the best ever plan, because looking for that will probably be a costly thing, right? But we have to avoid everything that is crappy. We have to avoid those that are really bad, that really take long, right? So we need a good plan, maybe not the best plan, maybe not a very good plan, but also not a bad plan, right? Good. So that brings us into our next detour, and we will show an example.
So to give you an intuition of what is behind query processing when we have a distributed environment, let's give an example. So we will use the same database with these three tables that we showed before. And now the query is find the creatures involved in fights being decided in exactly 1 minute. Now imagine that we already have the relational algebra expression. So basically a join between creatures and fights with a selection with the condition that we were giving in the query, just 1 minute, the duration of the fights. And then we just do the projection on the names of the creatures. But now let's make the problem a little bit more interesting. Now it is a distributed environment, so let's make the following assumptions. So relations are actually fragmented, and they are distributed, yes, just for the sake of the example, just 5 nodes, but imagine several nodes, and still the problem is, just to give you the intuition, right? 5 nodes. The creature relation is actually using primary horizontal partitioning. So this is one of the things that we did last week. Basically just looking at some criteria to divide it based on the rows of the tables, if you want to see it like that. And what is interesting is that we have one fragment of the relation in one node, let's say node 1, and the other part of the relation is in node 2. And we do not have replication. This is one of the things that we do in the example. If we do have replication, then it will be even more difficult to do. But anyways, no replication for the example. Then we have the files relation, and what we do here is, remember that we actually say, okay, once we do segmentation, fragmentation horizontally on one relation, we saw last week that the relations are actually related to each other. We have these foreign key, primary key relationships. Then when we have already one relation fragmented and we use another one that is depending on that because of this relationship, then we do derivative fragmentation. Yeah. Based on these pairs of primary foreign key, we actually do the fragmentation of the fights relation. And that means for the example that we have one fragment on node 3 and one on node 4. And again, we have no replication. What is interesting is that the query is actually originating from a node that has none of the information that is needed to actually do the query. This is what is interesting here. So this is the picture of what we have. The query is in node 5, right here. And node 5 has no idea of the data. The data is actually distributed, so we have the creatures table over here, and the semi-join that we did to do the fragmentation of fights is over here with respect to the creatures 1, fights 1, node 1 and node 3, and the same when we look at fights 2 and creatures 2. They are actually, the fragmentation of fights 2 was actually getting from the semi-join on creatures. Yeah? So this is what we have. Now we were talking about that there is always some sort of a cost model behind the optimization, and some statistic as well. And this is what we actually provide for our example. Let's say that this means the accessing tuple cost. And for the example, it's just 1 unit, whatever that unit is. We just say it costs us 1 unit. Transferring a tuple, we will put it like this, will cost 10 units. What we want to emphasize in the example is that accessing a tuple locally is cheaper than doing a transfer or a shipping of the data. And this is what we want to say here. If it's locally accessed, it's just 1 unit. If it's a transfer, it's 10 units. It's more expensive. And then let's assume some basic statistics of what is the size of the tables that we have for this example. Let's say that we have 400 creatures and 1,000 fights. And those that fulfill our query are actually only 20 fights. Only 20 of them are actually 1 minute. This is what the query is asking for. And furthermore, we assume that all the tuples are actually uniform distributed. And that means that the nodes that contain the fight table, we will have the 3 and 4 nodes, they contain half of the answers, 10 short fight tuples each of them. And then we actually have we know that there is a local index on the attribute duration, so there's no need for scanning if we do the access on the machines where the data is located. This is important, and you will see in a minute why. And furthermore, all the nodes are actually directly connected. This is what we have to emphasize here. Any access to any node is easily done. And so this is our query. We have 200 tuples on this side, 200 tuples on this side as well. And then we have the matches 10 over here, 10 over here. This is what we said in the previous slide. And now let's try to actually do two different plans. One is if node 5 is asking for this query to be answered, one thing that we might think, okay, let's then just send all the data, everything that we have, and let node 5 do the processing. This is the first plan. So that means that every single node will send everything that is required. We need the creatures table and the fights table. And we ship everything through the network. And then once it's received, the only thing that we need to do is to do union, because remember that last week we mentioned that if we do the fragmentation, one of the rules is to be able to reconstruct the original relation. So this is what we do by a simple union when we have horizontal partitioning. So let node 5 do the job to do the unions, and then do the selections, do the join, and do the projection. This is one plan. This basically ignores everything that has to do with the distributed environment. It's just keeping the data, and I will do the process. This is one plan. The second plan actually is a little more clever, because instead of shipping all the data to the node, what we do is we do local processing. And that means basically that node 3, before sending anything, will do the selection. And this is just a principle that it borrows from the example that we saw when we do a centralized query optimization. We want to do the selections and the projections first, because this is something very quick that we can do. Now in a distributed environment, we do it in a way that we know what's the condition in the query, we just ship what is needed for the query to go on. So this is what we do in node 3 and node 4. We do the selections over here, 1 minute, 1 minute. And even more interesting is, remember that we have an index on the local machines on this table. So the selection will be very quickly on these machines. And then what you do is just ship the answer to the queries of the fight selection to these nodes. Yeah? But we do it again considering that we did derivative fragmentation. And that means that these two guys, when we do a join, this will be very efficient as well, because we partition in that way. Then it will be faster compared to what would happen if you let node 5 to do the join. The same goes here. The join will be much more efficient, because we know that we did the partition basically thinking on these foreign key, primary key relationships. At the end, what we ship is only the results from the two fragments. And then the task for node 5, it will be just doing the union and doing the projection. You might imagine that if we compute the costs, what will happen is that for the first case, we have 23,000 units of cost. Why is that? Remember that we have 1 unit of cost if we have access at the top of the local machine, and 10 times when it's a transfer. So in the first case, we're actually sending everything. So that means that we have a 2,000 units here, because we are sending the 200 tuples to the node 5, to node 5. 200 times the cost of transferring every tuple, 2,000. The same goes here as well. And in those two cases, it's exactly the same. 500 tuples times the cost of transferring tuples will give you 5,000. Now when you have all the data on node 5, you have to do the selection, And that costs you 1,000 units of local access on the data that you have. And what is important is that you don't have the index. The index is in the nodes where the tables are. But in node 5, there's no index. So the selection will be painful, will be a scanning. The same goes for the join. It will not be efficient. So that's why at the end we have 23,000 units of cost. In contrast, Plan B, which was actually looking at the distributed environment, looking at the details of how do we do the partitioning, what kinds of indexes do we have, where do we need to do the joins, is actually 50 times cheaper than the other plan. This is a huge difference. And we observe at least 3 reasons for that. One is we have an index here. We do this very efficiently. So it's only 10 tuples that we need times the tuple access is just 10 units. Then we ship it to the node that is actually the one that we know that we partition on with the foreign key. Then here we only need 10 units to get from the creatures table and the 10 units that we have for the fights table to do the join. Then we have 20 access locally. And then we ship that to node 5. The same goes in the other direction as well. So that's why at the end, it's very easy for the node 5 to get just the union and get 50 times cheaper than plan A. You see it? So what we want to say is that if we exploit certain knowledge from the distributed environment, we can be very efficient in executing the query. Now, the question is, how do we know all these things? How do we know that there was a fragmentation, a derivative fragmentation actually relying on the keys? That meant that the join was very efficient to do. How do we know that there was an index on the machines that have the fight relations? How do we know these things? We know these things because we borrowed the idea of the catalog from the example that we provided at the beginning, in the classical way, how do we do it in a non-distributed environment. We borrowed that idea, but now that we know that in a distributed environment is more challenging, then we're adding more data to this catalog. So it seems that knowing what exactly is happening in this catalog, what kind of metadata that we have, makes a huge difference. And the issue of what is there is exactly what we're going to do next.
Okay, time to go on. So we've talked about, or Jose has just shown you, that there are vastly different query processing time, or there may be vastly different query processing time if you only have some statistics and some ideas of how to access your data and where to find data, how to ship very little intermediate data, right? And the difference between 460 time units, right, and 23,000 time units is considerable, right? Think as a time unit of like a millisecond, then 460 milliseconds is half a second and you get the results, right? Whereas 23,000 milliseconds is 23 seconds, so half a minute and you get the results, right? This is a difference, and this is a vast difference. Now you can say, of course, well, I mean, shipping all the data into one node is obviously the stupid solution, right? You wouldn't do that, but the question what data you can use for the optimization, right? And what data do you actually need to figure out what a clever plan is versus a not so clever plan, right? This is difficult, right? So in particular, you need all the data that has the information on data distribution. And the idea is exactly the same like in the centralized system. In the centralized system, you had a catalog of metadata, right? And the catalog contained all the schemes, which data is located where, the possible access path, right? Which indexes are on which attributes of the data, and maybe some more information. For example, if you have special types, if you have stored procedures, user-defined functions, what is the key? On the key, there's always a primary key, right? So can you read sequentially? Is a scan over this data cheap, or can you read? Do you have to move the reading head quite a lot? So is the reading of that data, a scan of that data, sometimes cheaper as using the index at all, right? Sometimes if you read enough data, a scan will always beat using an index if it's a secondary index, right? So all that information has to be collected. Of course, we need more. We need data on the basic partitioning, right? How data is partitioned and how tables can be reconstructed. So, for example, why did we have to ship so little data in the previous example? Well, because the creature table was horizontally partitioned, right? And the fights table was a derived horizontal partitioning, right? So the values or the entries in the fights table that belonged to the entities in the first partition of the creature table, right, was in the first partition of the fights table, and the entities or the records that belonged to the entities in the second partition of the creature table were in the second partition of the fights table, right? Otherwise, we would have to do a crosswise join. In that case, since we know the schema of partitioning and since we know how to reconstruct the schema, the schemas, we could only ship the first fight table to the first creature table and the content of the second fights table to the second creature table, right? So the partition schema and reconstruction information. Then the allocation schema, where is which fragment, and of course the replication of fragments. Do I have several possibilities of accessing that data? And if so, are the nodes where I have the possibility of accessing this data different in terms of their responsiveness, in terms of their computing power, in terms of whatever, right? Is it beneficial to get something rather from node 1 than from node 5? Because either node 5 is under heavy usage at the moment, so it will probably be slow, and node 1 is idle, or node 1 has a lot of processing power and node 5 is a cell phone, right, that has rather small processing power and nothing I can rely on really, or it does not have a stable connection or something like that. So the question, do I get different benefits out of the replication? Then, of course, the network information, latencies, delays in the network, everything that you need to know. Same here with the connection of the nodes, right? We assumed a fully meshed network. Every node can communicate with every other node, right? What if you have tree-shaped networks where you have high fan-in networks, right? A lot of sensors that are only sending to intermediate nodes, and those are aggregating the results, sending them on, right? So there are different network topologies that you need to consider, and then you need to figure out how to ship the data or where to ship the data to. And then there's additional information, for example, the information on indexes. It was very cheap to get the selection down to nodes, I don't know, it was 3 and 4, I think, right? Because there was an index on the creature. So we did not have to scan the data, but we could just have 10 tuple accesses, and that was that, right? So all that kind of information is very important. The central problem in a distributed database management system is, of course, well, you have the information on the distribution, and you have the metadata catalog, right? Is the metadata catalog in itself distributed, or is that in a central location, right? Of course, a simple solution is just put it onto a sampler node, right? If that node is under heavy usage, because obviously every query and every processing node needs the metadata, then you can replicate it and put it on several nodes in the network, so everybody has cheap access to the network. That is replication of the catalog. Then, of course, you could say, well, as opposed to the actual data, the metadata is not so big. So maybe you put it on a central node, but at the beginning, when you start up the network, when you start up your database, every computing node caches a version of it, right? So everybody has a local version of the catalog. So caching is a viable solution. On the other hand, right, if you cache something in different spaces and it's updated in the central space, something changes, right, then this change needs to be propagated to all the cached version, to all the replicated version. To the replicated version is easy because you know where they are. To the cached version, you need to know when was the caching actually performed, right? So is that a stale version, or is that, did the node just get the data and already has the new version, right? So this communication needs to be done. In the worst case, if you have a lot of data, a lot of access paths, a lot of stuff, right, then even the catalog is fragmented and distributed, right? You have to live with a distributed catalog. And the question whether you can do that in a sensible way, or if you just move the problem of distributed query processing one level up and say, okay, now it's distributed metadata query processing. I did not solve the problem at all, right? But I just moved to the level and then I made the data a little bit smaller, right? We will see in the following, not in this lecture, but 2 lectures on, we will see distributed ledgers and distributed procedures where you actually can fragment metadata catalogs and then get the best of both worlds in a way, right? Okay, so then you have the question of when do you optimize and where, right? And what you have very often, think about the web or something like that, right, is what we call canned queries, right? So it's basically not a query that somebody typed in and created for that purpose, but it's a standard query that is, for example, a database lookup in a product database, or, you know, some request on I don't know, friendships requests on Facebook or something like that, where the structure of the statement is quite clear, and also how to optimize it is quite clear. So very often we're talking prepared statement. However, parameters may change. Yeah, you want to buy a different product, or you want to look up the reviews for a different movie, or you want a recommendation for whatever, right? So the basic query is always the same and is a certain task in your application. However, the parameters may change, so everything is pre-computed, right? So then there are different possibilities of working with that. There's the full compile time optimization, right, which is exactly the same as centralized databases. The query is passed, the query is pre-processed, the query is optimized, and then you can do whatever you want to. On the pro side, we have direct execution of every query, and you have the flexibility of writing every query that you want to. On the con side, well, you have very complex models that you need to do, and you need to do all that optimization, which costs time, especially since not all the information, network latencies and so on, all these things with a high variance, right, needs to be known, needs to be gathered, right? So difficult. Outdated statistics may play a role, right? So network properties, machine loads and something like that can be measured at every point in time, predicting them. difficult, more difficult than actually measuring them. Or you can have a fully dynamic optimization, so not at compile time, but at runtime. At runtime, I said measuring is easy, predicting is difficult, right? So the statistics get better, the variance gets lower, because if I just do the prediction for the next second, it's much easier than doing the prediction for, and in half a year it will be the same, because I prepared the statement at some point in time, half a year ago, when I said every user doing this and that, looking up a product or whatever, executes this query with different parameters, right? So on the pro side, the plans are probably better when you do it at runtime, right? And you can measure all the information, all the statistics that you need. On the contra side, right, it's kind of unpredictable how long that will take, you know, because this is runtime, this is response time, right? Maybe the plan is better, but is it worth it, right? Is the amount of time, response time that you save by having better statistics, by having better optimization, right, of the statement, really worth spending the time to optimize it? Or shouldn't you have spent the optimizing time half a year ago and then live with the mediocre plan with outdated statistics and so on? Right? It's difficult. It's a decision that's very hard to do. The truth usually lies in between, right? The truth lies in the middle. So what most optimizers do is kind of like a semi-dynamic or a hierarchical approach to do that, right? Things that do not change very often, for example, the partitioning schemes or something, or whether there's an index or not, are separated in the optimization from things that do change very often, like the network delays or the latency that is in the network these days, right? And so a semi-dynamic approach is to pre-optimize the query, and then when the query actually arrives half a year later or whatever, right, then you test if the execution actually follows the plan, and if the network still has the predicted properties and so on. And if you see there are a lot of deviations, right, so the plan does not seem to work very well, then you compute a new query plan for what you deem as being wrong, right, and you merge the query plans. So this is kind of like the semi-dynamic. You build on a skeleton that is has been pre-optimized, right? And all the pieces where the execution, during the execution, you see it does not fit, you re-optimize for the next queries, right? Hierarchical approaches are plan creations in multiple stages, right? So they're so-called global local plans, where the global query optimizer creates a global plan, which is usually concerning the data shipping, actually, which node does what, right? So the things where you know, okay, this data always resides on this node, or this data is partitioned in 3 partitions on these 3 nodes, or something like that, right? And then for the local behavior, you have local query optimizers that then talk about indexes, that then talk about how a join is actually performed and so on. But they are only concerned with what happens on that node, what happened or between 2 nodes, right? Not with the global shape of the queries, because they can obviously get very, very difficult to see. Another kind of hierarchical optimization is 2-step plans, right? Where you say, well, I do have a stable part of the query, right? And I do have a a part of the query that needs to be changed every time, right? That is rather unpredictable, right? And then I will say during compile time, I only will compute the stable parts, a skeleton for the query that is always done like that with the join orders, for example, right? Or the join methods. And during query execution, the missing parts of the plan, so the unstable plan, parts of the plan that are quite unpredictable are recomputed, right? And for example, the transfer over the network or which nodes are selected depending on their workload, on their current workload, and so on, if you have replication of data, right? So you basically have a skeleton of the query, and then you put in those parts where you say, okay, where does the data actually come from, which replication is used, right? And both steps can, of course, be performed using traditional query enumeration techniques. So if I talk about join order optimization here, right, then dynamic programming comes into the game. And spending that once, not every time I do a new plan, right, definitely makes sense, because the statistics of the tables themselves that you're joining will not change that much over time, right? They're growing, but probably not changing their proportions, right? The table that used to be the bigger table will not all of a sudden become the smaller table, right? So, but it will rather stay stable. Much easier than full optimization, of course, right? Because all those parts where you need to estimate the network delay, where you need to estimate the load that is currently on a node and so on, are not considered in that optimization. So this is kind of interesting. And then for those things, you have fresh statistics at runtime. Yes, please.
Maybe a short question.
Yes.
Plans are quite static, I would say.
These plans to some degree are static because the statements are prepared, right?
Is it an option to update these plans, for example, with machine learning algorithms?
Of course. This is very, very often done actually, that you learn some statistics or that you learn some properties of what you do. But again, machine learning costs time, right? So when do you do it, and on which part do you do it, right? If you're talking about a full optimization that you prepare, then running a machine learning algorithm in the background, collecting data, collecting statistics, and at some point when the machine learning algorithm says, well, things have changed quite a bit, please re-optimize, right, is probably a good idea. On the other hand, doing machine learning and data mining and all kinds of different things on the fly at runtime may be a little bit heavy-handed, right? Because you need to be fast. You need to, the user expects an answer now, not in 3 seconds. Now.
A whole copy of the data set could be an option to train on this data set, and maybe then
offline, right? I mean, and you have the same problems as ever, right? Of course, you can do a full copy of the data, but the moment you make that copy, it's stale, right? If you update it whenever an update happens in the real world, right, then you put stress on the system, because then the real system does not only have to do that update, but also has to figure out that the stale copy needs the update too. So you have 2 updates basically, right? There's a little bit what you do in data warehousing, right? In data warehousing, you draw a copy of the operational data, right? But you don't want to put stress on the database, on the operational databases. You cannot kind of compute complex things on that original data. So you make a copy, and that copy becomes stale over time. And then every night or whatever, when there's time, or between Christmas and New Year, when your company is on holiday anyway, right? then you refreshen your view of the data. Yes?
I was just thinking about these plans because I read an article where they are saying, where they are explaining the Google search algorithm. It's quite a famous algorithm at the world, I would say.
Mm-hmm.
And they are saying that if you have a traditional plan or a two-step plan or whatever, you have an input, then you compile a plan, and then you have an expected output. But the expectation of the output is not, or even the Google agree, is that you cannot say what's the expected output because they are also using machine learning algorithms. And in some case of search functions, they can't test it anymore because the machine learning algorithms are, they are quite complex. So the output plan is not the really expected.
Well, there's a difference. There's a difference between the semantics of the output, right? What do you want to be retrieved? And how do you retrieve it, right? The semantics of the retrieval process, right? And of course, I would agree that the semantics of the output may change over time because people mean something and then they would rather like this than that, and you have all that personalization and stuff, right, that you can learn. But for the execution of queries, it's you rather learn the parameters, right? You can learn something that a query that runs at night is much quicker than a query that runs over the day when everybody's running queries, right? Or that people over lunchtime don't do shopping, so queries are executed faster, usually in a time window between 12 and 2 or something like that, right? These are things that you can learn from the data. Things like network latencies and when there's peaks in the latency and when there's low latencies usually, right? And then you can start distributing your queries in a way that it fits, that it optimizes the overall throughput, right? If something has to run right now, you're kind of like updating your shopping cart or something is a query that has to run right now, right? But some queries can actually wait. So, for example, when you paid in your shopping cart, right? When the actual transfer is done, that can be done during the night, right? You will not be unhappy if the money is kind of like deducted from your accounts an hour later, right? So it depends on the semantics of the query, when it should be executed, but with respect to the optimization of queries, right? The question what you can learn and what you have to get fresh from the current behavior of the network very much depends on what you're trying to do. Good? Very well. Okay, so first problem of distributed query processing is data localization, right? Where is my data? The user wants all the creatures or all the files. Where is that data, right? How do I find it? And of course, if you have distributed nodes, each node needs to know what the other nodes are about, right? So in a perfect world, you would have query transparency, something like a global schema over the whole database, right? Everybody knows everything. Shared knowledge, total shared knowledge. However, of course, the relations are fragmented and distributed, which is the whole point of a distributed database, right? And if something changes, it's not my problem because it happens on a different node, right? But if I want query transparency, I should know about it. There's a problem, right? What should I know? What do I have to know? And you can make several assumptions that help you to get around that problem. So one assumption is that there are partitioning rules, right? That the things are not distributed randomly or by chance, but there are certain rules how things are partitioned, right? So, for example, the predicates of selection for horizontal partitioning, you know, that the data from A to D is on node 1, and if new data arrives at under D, right, then it will be on node 1. So you can see from the query semantics where to access this data, whether you know what's happening or not, right? And the data from E to F is on node 2, right? And so it's kind of partitioned by rules, right? And selection predicates for horizontal partitioning allows you to ask for tuples, right? Attribute projection for vertical partitioning separates the columns from each other, right? Let's assume that we have only each fragment once, so there's no replication, and that the fragmentation rules and the location of the fragments are then stored in a catalog, right? Then the base idea is that we have the query rewriter as a central component in such a way that each query saying, I want all the creatures or I want all the fights, is immediately rewritten to I want creatures 1 from node 1 and creatures 2 from node 2 and fights 1, 2 from node 3 and fight 4 from node 4, right? And knowing the rules of distribution, I know where the stuff is and I know how many fragments there are, right? So each reference to a global relation is replaced by a localization reconstructing the actual table. And those are the unions that you saw in the query before, right? Where we said, well, basically the creature table is a disjoint union of creature 1 and creature 2, right? If the localization program reconstructs the full relation, we call it a generic query, right? But very often the full relation is not necessary. Think if we have a rule, all data from A to N is on node 1 and from O to Z is on node 2, right? Then I don't need to reconstruct the full data. If my query goes, okay, data between E and H, because I know that is in one partition only, right? I don't need the second partition at all because there can no relevant data can be in that second partition, right? So sometimes it's not necessary to build the full relation, right? And there are certain reduction techniques where you can say I don't need that part of the data. Okay. Example, we have the creature table, right? A global table, CID, CNAME, and type. Now we do a primary partitioning by ID. The creatures lower than 100 are on one place, between 100 and 200 are on a second place, over 200 are on a third place, right? Let's not talk about load balancing now, so we get more information, we get more and more creatures. They will all go into partition 3 now, right? Which is kind of not what we would like, because then partition 3 is growing and the other partitions stay stable, right? So at some point you will have to change the rules and reshuffle. But still, let's not talk about load balancing at the moment. Then we allocate each fragment to its own node. Creature 1 goes to node 1, creature 2 goes to node 2, creature 3 goes to node 3, and so on. And then a generic localization feature for the whole table, for the global table, is simply the union of the 3 tables, right? So get the data from node 1, get the data from node 2, get the data from node 3. You have the full table. Okay? Global reconstruction. My query says, I only want the creatures between 25 and 75. Do I need the full table reconstruction? No, I just need the first fragment, right? So, global queries can easily be transformed to generic queries by replacing the table references, creatures, right, by the localization query places, and then you just put that into the generic query. Everything else stays the same. Just have this new part. Clear? Good. Often it is not necessary to get the full table reconstructed. So if you use generic queries, unnecessary fragments might be transferred and accessed, right? So we can use knowledge about the partitioning to reduce the query, right? Reduce query, CID is 9, can only be in the first fragment, right? I don't have to think about fragments 2 and 3. Good? Right. So, in general, reduction rules for primary horizontal partitioning goes as a selection, right? The fragments of the table are n fragments, where each fragment is built by a selection on a certain predicate, the rule, right, on the full table, on the global table. Clear? Reduction rule 1, all fragments for which the selection is empty, right? So the rule says those go into partition X, but the statistic says there are no objects of that type, right? Can be directly omitted from the localization program, right? And the empty set can occur in different ways, right? Either it's the wrong range, right? I have kind of like the selection says ID is 5, but the selection rule says the number of IDs is between 100 and 200, empty set, right? Immediately. So the selection with the query predicate on the fragment will be empty if the query predicate contradicts the partitioning predicate, right? ID is 9, ID is larger than 100. Contradiction. Good. You can do join reductions, very similar to the selection reduction. Join is a selection over a Cartesian product, right? So the idea is that if you have larger joins for the complete table, you can also build smaller joins of the fragments. So the global table R is joined with S, is exactly the same than joining the first partition of table R with S and joining the second partition of table R with S and then doing the union, right? So this can be distributed and this might or might not be a good idea depending on the data and what you have. Sometimes it's better than to first union the tables and then do the join, than doing the individual unions, right? Of course, for the reduction purposes, if you know the data that you're interested in is only in R1, then first unioning and doing the join is always worse than doing the join only with R1 and omitting the join with R2, right? So all the union fragments from the evaluation which would return an empty result are omitted. Good. So join according to a join graph, right? Well, usually you don't know the join graphs in advance because you don't know how many tuple on each side will actually join, right? But let's assume we know the join graph. Then the discovering of all the non-empty partial joins will construct the join graph. So for example, I know that there are items in R1 that have a partner in R2, right? And then we have to do that join, right? So this is the join between the two of them. And if I know there is no object in R3, or there's no object in S1 that has any connection with an object in R2, so it hits empty here, then I just don't need to do that and can omit the join. So the question which fragments I have to join, which joins I have to perform, depends on the overlap of attributes in those fragments, right? Clear? Good. Well, the hope that you have for the data location is, of course, that many partial joins can be omitted, right? So I don't have to do them. Joins are always expensive, because usually if they are done in a distributed manner, if the data resides from both tables, right? The data resides in one node and the other data resides in another node, then I either have to ship the data from here to there, or I ship the data from here to there, or I have a third node doing lookups on either node, which is even worse, right? So everything that can be omitted is usually a good idea. Of course, if you have small relations, then the join costs may have lower resource costs than a single large join, right? Talking about things like block nested loop joins, like an index nested loop joins, yeah, also depends on that. Of course, for this you need sensible partitioning condition. And again, it depends on the join algorithm and the data distributions that you have, so it may not always be true, but still, as a heuristic, it works out. And one advantage that you have, that doing the individual joins, the smaller joins, allow for parallelization. So basically what you get is a bushy join tree, right? You don't have to join, like the full tables only and then ship the data somewhere, but you can, if the network is not yet fully loaded, you can use intermediate processing nodes to execute some partial join, and at the same time other nodes to produce the result of other partial joins, and then you ship the results together, right? So that is kind of like very sensible usually, but then again there might be selections that work on both fragments of the join, so doing those first on the full relation would be beneficial. So it's not always a good thing, but parallelism usually decreases the response time, right? So it's a good heuristics again, right? On the other hand, you have more communication costs, so depending on how expensive it is to ship the data and to reunion the data and to synchronize between different nodes, right? But still, good heuristics anyway. Let's do an example for data localization, right? We have the creature table, we had that before, and we have these three splitting conditions, right? And we have the fights table in two places, those with CID smaller than 200 and those with bigger than 200, right? And now you see that we have kind of like different matches, right? So this match over here basically goes on those two tables. However, there's a smaller here, right? And this over here works only on this one, right? Because it even includes the equality, right? Okay, then let's do the select star from creature C, find F, where CID is CID, right? Global query. Everything together, 3 union parts here, 1 union part here, right? Generic query gives us exactly that. Now we could also do the splitting of the joins and see which parts of the joins are empty, right? If I split the join, this goes here, this goes here, this goes here, and this goes here, this goes here, this goes there. There are 6 small joints that we have, right? Now the question is, which can actually join? Those were the one over 200. Those were the one under 100, and those were the one under 200. Can they join? They can never join, right? Because the predicates do not match. The set between the predicate is already empty. So actually, there are 3 joined fragments that are empty. So the only thing that we have to do is join those 2, join those 2, and join those 2, right? And then we got it. Okay? Clear how it works? Good. Formally, joint fragmentation. If I have a union of partitions and join something, I can do that small and join afterwards, right? First join the partitions, then join afterwards. Reduction rule, if I know that some partitions do not overlap by their splitting predicates, I know that the join results they will produce are empty, right? Then I can omit them from the joining. The join of the fragments Rj and I will be empty if their respective partition predicates contradict. Same as we had before. Empty joint fragments, kick them out. We don't need them. Good. Of course, the easiest join reduction is if you have a derived horizontal fragmentation. Jose had that in his example, right? Very clever. He did not have to do all the intermediate joins, creature 1 and fight 2, and fight 1 and creature 2, right? Because the first entries in fight 1 only reflected the first entries in creature 1, and the entries in fight 2 only reflected the entries in feature 2, right? So the fragmentation were dependent on each other, right? So if you have a derived horizontal fragmentation, for each fragment of the first relation, there's exactly one matching fragment of the second relation, right? The square-wise joining becomes linear, just one by one, a one-on-one dependency. So reduced queries will always be more beneficial than the generic query because you can omit almost all joins except for the direct matches, right? So this derived fragmentation is especially effective if you have one-to-many relationships, right? Because if you have many-to-many relationships, then the joining might work over all the partitions, and then you gain nothing from doing small joins, but would rather do the big joins, right? So if you have many-to-many relationships, the probability of fragment disjointness, right, is rather slim. On the other hand, if you have one-to-many or one-on-one relationships, best case one-on-one relationship, right, immediately get the derived horizontal partitioning from that. Good, example. Like we had before, the creature table, the fights table, right, select star from creature and fight where the CIDs match, right? The reduced query is no longer quadratic. Everything has to be matched with everything, but the first of creature is matched to the first of fight, the second of creature is matched to the second of fight, third of creature, partitioning of creature is matched to the third partitioning of fight. That's it, right? No cross products anymore. Creature 1 and fight 2 cannot match. They will not produce results, so we just omit it. Good. Now, we were talking about horizontal partitioning and the selection process. Now let's talk about vertical fragmentation, right? And it's kind of the similar thing, only that you don't use the selection, but you use the projection, right? You're talking about distinct columns, not distinct rows. Good. So the localization program is usually of the form join of two partitions, and one partition has columns 1 to I, and the other has columns I plus 1 to n, right? So the table is somehow split column-wise, right? And of course, when you do a vertically fragmented query, then the attributes occurring in that query will directly tell you which fragments of the table you actually need, right? Because why should you look at fragments that do not contain any attribute that you either need for joining or that you need for selection, right, or projection? If the attribute does not occur in the query in any form, why would you need it? Why would you need that partition, right? Just omit it. So same thing here. Let's assume, very simple, we have creature, CID, CNAME type, right? It's only 3 attributes, but for the sake of the example, right, we split it in CID, CNAME, and CID type, right? So we can put it together again because both have the CID key in it, right? And then one has the CNAME and one has the type, right? So if I have the query select CNAME from creature where CID is 9, why should I look at that table, right? No reason whatsoever. Shipping that data is totally useless because it just contains type data, right? So we won't do that. Same thing. Now let's look at hybrid fragmentation, right? Let's see that the localization program, like we had, was consisting of the reconstruction of a table, R1 union with R2, and then a third thing is joined on top of that, right? So there are again, the same guidelines apply as we had before. So if we have empty relations, right, that are generated by contradicting selections, just remove them, right? All the relations containing tuples that you will never use. If you have vertical fragments whose attributes you don't use, right? Just remove them. You couldn't care less for the values of that attribute, right? And then finally, if you have empty fragment joins between fragments that do not produce results, that cannot produce results, right? Just break them and don't do those parts that do not produce anything. Okay? Simple localization rules. In all these things that we did now, we looked at reduced queries from the global query, right? But one question that we did not look at yet is where the query should be executed. Because if you have 2 fragments, chances are they will be on different nodes, right? So they will reside on different nodes, so you can do the computing in either node. I told you before, or in Jose's example, it was before, that a third node actually gets the query, right? And then there would even be a third node involved and say, okay, you both guys ship the data to me and I will do it. We saw that this is usually not a very clever idea, shipping all the data. I mean, yes, if all the other nodes are loaded to the end, right, and then it might be sensible, or this node that gets the query is a super node, right, with where everything runs a lot faster, then still might be sensible, but usually data shipping is to be avoided at all costs. So let's assume we have these two nodes having the two fragments. Either one can do that, right? And this is the typical client-server setting that we have, right? The server stores the data and a query originates on the client. Then you can basically do a couple of things. You can do query shipping, right? So the query comes in somewhere and move it to the fragment, right? And it's evaluated at the fragment. So you send the query to the server node, server computes the answer and ships back the answer. Why does it do that? Well, because answers are usually much smaller than the original data. So shipping the original data for remote processing is more expensive than shipping only the answer set plus the query set, right? So the sum of both is much less. Second thing is data shipping. The query remains at the client and the server ships all the required data to the client. Then the client puts together the result, right? So here's the query. In the query shipping, the query is sent from the client to the server, executed on the server, right? So the query is shipped and then the result is shipped back. Data shipping, the data, the client keeps the query, right? The data is shipped to the client, right? Here's data. And the client is shipped to the data here. And then the client can perform the query, do whatever, and computes the result. So the result does not have to be shipped. If the combined data is smaller than the query plus result set, you got a deal, right? Usually that will not be the case. Base data is usually much bigger than result sets. Okay? Good. Then there's hybrid shipping solutions. So maybe you give part of the query to the server and say, well, instead of shipping all the data, maybe the selections can be shipped to the server already, and then only few data is shipped. So this is kind of few data, and this is also kind of few data, right? And this is kind of small query. And same here. Okay? So truth is in the middle, right? Could be worthwhile, could still be a lot of data that you ship because the join might actually eliminate a lot of data. I don't know, right? Depends on what you do. But those are the basic solutions. Now we talked about client-server. The client gets the query and the server has the data. Of course, now if you fragment the data over multiple nodes, over multiple servers, works exactly the same, only the shipping gets more complex and you need that localization with the unions to reconstruct the tables, right? That's it. So it's very simple to extend those queries to multiple nodes, and the query optimizer needs a cost model to figure out what should be shipped and what should be pre-selected and what should not be shipped, what doesn't have to be shipped, and so on and so on and so on, right? Also then, in heavily replicated scenarios, you can allow for a certain kind of load balancing by this. So the computing intensive parts of the query can be done by queries, by clients, right? And the pure data manipulation and data filtering things can be done by the server. So you don't overload the server with query tasks, right? But you don't ship too much data either. So a certain kind of load balancing, avoiding too much data shipping, but minimizing the communication costs can be used. So the last thing we want to do today are response time models, and the idea also comes from the classical databases. So if we look at normal databases, then the cost model that is used is a mixture of different times that are needed, right? So you have the number of disk accesses that is usually minimized. Why is that? Because every disk access costs time to allocate the reading head, then the time that you need to read the data, and then the time that you need to put the data into main memory, to ship the data to main memory, right? So the cost model of the query processing is how many of those data accesses do you need, right? And how long does it take, right? So it's usually kind of time-based. And this leads to very good results if you have a lot of computation, because computation in main memory is cheap, right? And on the other hand, slow network connections. Reading from disk is cheap. Shipping data over the network is cheap, right? If the query saves some resources, you have a higher throughput. You can execute more queries in parallel on your system, right? So getting the total throughput is a secondary optimization goal. Of course, throughput is not always what you are interested in, but very often you are interested in the response time. Think about the Amazon scenario, right? Rather build more infrastructure than letting people wait until they can do something in their shopping cart. Because if that takes too long, or the search for a new product takes too long, they might just leave. They might just, lose interest and then say, okay, I have something else to do. I cannot wait for this thing all day long, right? Get to a new shop, or kind of don't buy anything anyway, right? We have enough stuff as it is. So in many, especially cloud-based solutions, this response time is the main thing. So you could waste some resources, so computing resources, or even network transfers to get the query results quickly, right? And that means especially that you need this kind of load balancing that I just talked about, right? Because if you have the server, a single server, or a logical storage area network, right? And then you start to hammer a server, right, with more and more load, then the whole thing will become very slow, and each individual query will become very slow, right? So this is kind of like not the idea, but the idea is that you use all the resources that you have in the network in a balanced way. Instead of parallelizing each query, so the concurrent queries on different nodes, executing them on different nodes, it might be more beneficial to parallelize parts of each query on different nodes rather than different queries on different nodes, right? To gain parallelism and to do fragmented joins in parallel, for example. And for this, you need so-called response time models. And response time models basically address two questions. And the first thing is, when does the first tuple actually arrive, right? And this is what is usually called online algorithms, right? In classical databases, you usually talk about query times, right? How long until a query is executed and you have all the results, right? But if you think about it, if you think about the online world, right, and how web pages are dynamically generated, then maybe it's more beneficial to have the first 3 products on that web page at an early stage, and then the last 3, 4 can wait, instead of having all 6 in okay time, right? So sometimes it's beneficiary to sacrifice some total response time for fast, quick results, because then the user has something to look at and can already play with it, right, and see, oh, is this what I want, or is the next one what I want? And until, since the user's still deliberating, you know, in the background, you get the second page of results, or you get the third page of results that was not ready when the user first entered or saw the first results. So the distinction between when does the first result tuple arrive and when have all tuples result, so when has the query finished, especially in online scenarios, and those are most distributed scenarios, right, is really meaningful. Let me do an example, right? I have relations of fragments A, B, C, and D. And assume that all the relations and fragments are available on all nodes. So I do a full replication over my network. I have full computing power in every node, and every node has the data. So now what I want to compute is a full join of everything, right? And we assume that each join costs 20 time units, and transferring an immediate result also costs 10 time unit. Accessing the relation, we have indexed them all, right? So that's basically free. And each node can do 1 computation at a time. Let's look at it. We might have 2 plans. We execute all the operations on 1 node, right? And obviously, this node can first do this join. Since this is only 1 thread, it will then do the second join. And having both results, it will finally do the third join, right? So the execution costs for every join are 20, right? So total costs are 60. Now, let me do the thing a little bit different. I ship the results to a third node. So the first join will be done on the first node here. But at the same time, I do a join at the second node. Now I ship the data to a different node, and when the data has arrived, I will do the third join, right? Considering the costs, this is 20 again, this is 20 again, and this is also 20, but now come 10 for shipping here and 10 for shipping here. Okay, so 80. It's more expensive, right? But seeing what I did in arranging the operations, what we see is that node 1, everything is done on 1 node, has to work sequentially. Whereas I always said, well, these nodes and the shipping can actually be done in parallel. So the 30 time units that are necessary to do that have to be spent twice, but at the same time on different nodes. So for the total time, you only have 50 time units instead of 60, right? The waiting time until the results are ready, until the first result is produced, is much smaller, right? Because in the second part, or in the first part, you can only produce the first results and output the first results after both joins have been made, have been completed, 40 time units. In the second thing, already at that stage, 30 time units, you can start producing results. Good? Clear? So it really depends on how you model time and what you are interested in. Are you interested in complete throughput? Then you change the plan with the lowest sum of costs. Are you interested in in low response time to the user? Then a lot of parallelization might actually be worth higher total costs. Good. So, first types of response, two types of response time: time to the first tuple, full result response time, and the full result response time is the sum of what you get. For computing response time, you have to look at sequential execution versus parallel threads, or what you can do, what you can execute in parallel. If you do something sequentially, the costs add up, right? If you do something in parallel, you take the maximum of costs until synchronization as the costs of wall clock time that has been used, right? Difference. Sequential means summing up. Parallel means using resources as a sum, obviously, right? But in terms of time, the maximum duration of either of the parallel components is used. Good. Considerations: how much speed up is actually possible due to parallelism, right? Can we parallelize everything? Or on a different note, how does the kill it with iron strategy work, right? Because that's what you always hear. Well, then we take more computers, then we take bigger units, right? Kill it with iron, right? We will just have the machinery, and then the problem will not be a problem anymore. You actually hear that quite a lot when talking about complexity theory, and this all NP complete problem versus polynomial problem, and people say, well, I don't care whether it's NP complete, I will just throw more machinery at it, right? I will just kill it with iron. And to some degree that works, but we have to see that also the problems are getting more complex, so the P and NP classification still has it's beauteous. And the idea of parallelism was already investigated in the 60s, basically, and one of the central results goes back to Gene Amdahl, and it's called Amdahl's law. And he was looking at sequential code fragments in program execution versus parallel code fragments in the execution, right? And the Amdahl's law basically says that the time of the longest running parallel code fragment gives you a minimum for the execution time of parallelism, right, of a parallelized program, and so on. The total execution time of problems of programs is dependent on the longest sequential part of your program, right? So if the degree of sequentiality in your program stays the same, parallelism does not bring you benefits. That is what he basically said. So he said the possible maximal speed up that you can use is limited by the number of parallel thread divided by, well, basically the percentage of single threaded code. So if 10% of an algorithm is sequential, the maximum speed, it does not matter how many iron you have to kill it, right? How many computers you have, to how many units you can distribute it. The maximum speed that you can get is 10 times, right? 10 times until you need the next synchronization between the parts, and then you had the longest running part of 10%, right? This is one of the problems that the community in programming looks at currently, because the automatic distribution of program code, the automatic parallelization of program code, is a big problem. It would, of course, be wonderful having all these new wonderful multi-threaded processors and double core, triple core, quadruple core, whatnot core, kind of things, and with the GPUs and whatnot, loads of possibilities for parallelism. How can I put in a sequential program, an algorithm, and then automatically the system figures out how to cleverly distribute it, and then you get the fastest algorithm ever? Is kind of problematic and is limited by Amdahl's law. So, one thing. To give you an impression of Amdahl's law, right? So here's the number of processors, right? More and more processors that can all do individual threads, right? And then you have the speed up factors, and I have programs with different, or queries, if you wanted, with different parallel portions, right? You see, if you have 50% of sequential code and 50% of parallelizable code, right, then the maximum speed up that you will gain is basically 2 times, right? If you have only 25% of sequence code and 75% of parallelized code, you get 4 times already, right? But even if you have 95% of parallelizable code, right, and only 5% that needs synchronization, that is still sequential, it stops at 20%, right? And even if you throw more and more processors at it, it does not help, right? You can stop right here, right? It will not, no matter how big the program is, or it will not help. Putting more processors, like killing it with iron, will not help, right? This is Amdahl's law, basically. Kind of interesting to see. Good. So good first tuple response time benefits from queries execute in a pipeline fashion. Well, parallel and pipeline. What does pipeline mean? Well, usually, if you have different operators, right, you do a selection and then you do a join and then you do a projection or something like that. The join waits for the selection being completed, and the projection waits for the join being completed, right? And then the complete intermediate results are given, and then the projection is done, or the join is performed, or whatever, right? However, sometimes you can just work on data in a pipeline fashion, right? So consider, for example, you have data, relation R, and then there's a selection on top of that relation, and then there's another selection with some, here's condition 1, and here's condition 2, or something like that, right? Then the tuple is taken from R and is put into the selection, right? First selection. And now I store it as an intermediate result and get the second tuple from R. Do the selection with condition 2, store it in the intermediate result, and so on, right? And the first time that selection, the second selection with condition 1 is used is after the selection with condition 1 is fully is ready, right? Is completed. Now what I could also do is I could give a single tuple to condition 1, and being completed with a tuple, I could immediately hand it on to the second selection and even output it to the user, and then get the second tuple from R and immediately get it on, right? In that way. So either I do that tuple-wise, which is called pipelining. So I put the tuple into a pipeline, then all the selections are one by one streaming by, performed on the tuple. Or I do it batch-wise, full batch of relation R is selected for condition 2, and that batch, the selected batch, is given over to selection 2, checked for condition 1, and then output. Right? Two different things away. One is not pipelined, right? Intermediate results. One is pipelines. The tuples kind of flow through the operations. Each tuple is subjected to different operators, one after each other, without ever stopping in an intermediate result. Good. So usually tuple flows are controlled by iterator interfaces, right, where each operator has the next tuple command. And you see what's happening now concerning our discussion of sequential code and parallel code, right? Because if I have sequential code, right, and only a single thread, it does not really matter whether first I produce something and then say next tuple, right, or whether some things are computed at the same time, because that does not work. If I have multiple threads, if I can compute things on different nodes, in different threads, right, then of course the second operator in the pipeline saying next tuple every time he's empty, right, is a good thing, because it parallelizes the execution, right? So this is kind of the idea. Of course, if the execution speed of operations in the pipeline differ, then you need some intermediate storage. You need a priority queue or something like that, right? Where the tuples add up and then are taken one by the next operators. There are more expensive predicates like joins. There are simpler predicates like selections, right? They work on different times for each tuple. So definitely. So very good operations for pipelining are scan operations, selects, projects, unions, everything that you would think of. Tricky is kind of like joining or intersecting. Very hard is things like sorting, right? Because sorting before you know what is coming, right, is kind of difficult. But people worked on that. So pipelining is usually a good thing. Simple pipelining example: table scan, selection, and projection. So it's simple. It's kind of similar to the example that I just showed you. You have a table down here, you do a table scan over the table, get all the data out of the table, put it into a selection, and then put it into a projection, right? So at time 2, the first tuple arrives in the intermediate result. Then at time 2000, so if you look at the time table here, right, at time 2000, this is full, right? This is all tuples have been processed. So at time 2001, this whole thing goes into the select, right? And then it stays there for 1,000 things, right? Until this is kind of like everything goes into that intermediate result, right? And then at time 3000, it goes into the projection, right? And so on, right? It's clear. So at some point, sequentially processing that, it will arrive at the user. If you build it with a pipeline, every tuple that is built here goes into the selection, and every tuple that is produced here goes into the projection, and every tuple that is ready goes into the final output, right? So at time 2, the first tuple finished the table scan. At time 3, the first tuple finished the selection. At time 4, it went through the projection and is in final. So 3001, first tuple in final, 4, first tuple in final, right? Until the last tuple has processed is obviously the same time that you need, right? Because the operators don't grow faster or something. It's just the order in which you are processing things. And as I argued, it may be very interesting for users to have first results at an early stage. Good? Clear? Good. Okay. That this is actually an interesting thing can be showed, for example, at join orders. So let's look at block-nested loop joins that are non-pipelined and pipelined, right? So we have the table scan, selection, projection that we just have, and both produce inputs for the block-nested loop joins, right? So 1,000 tuples are scanned in each pipeline. Let's assume a selectivity of 10%, so 100 tuples have to be joined, and joining 100 times 100 tuple will give 10,000 time units, right? So every join is one time unit that we need to figure out. Then the response time for the non-pipelined part, right? So non-pipelined means intermediate result here, intermediate result here, and then we have the full result here, goes into the block-nested loop, right? Same thing on this side, right? Goes into the full nested loop. First tuple can arrive at any pipeline after the 4 tuple units stored in the intermediate result, and we have to finish the whole thing, right? So the total amount of tuples are here after, what did we say, 3,100 time units, okay, right? And then the final result, joining everything, will be 13,000 time units, basically, right? There's no benefit whether this has been produced with or without pipelines, right? No benefit at all. Now let's execute the thing with a pipeline join, because if we use the unpipelined joins, we would have to wait very much, right? So the problem of joining is, how can I do that in an unpipelined, in a pipelined fashion? Because usually I take a tuple from the first relation and compare it to all the tuples in the second relation until I know whether it has a join partner or not. I output those join partners, I throw off the tuple, take the next one, compare it to all in the other table, right? Finished with it, throw it away, take the next one, do the same thing again, right? So joining is quadratic. And I need to know from one tuple that I have, I need to know all the tuples on the other side, right? So this is why most traditional join algorithms are kind of unsuitable for pipelining, right? But if you have pipeline joins, then you can exploit all the parallel execution and the distributed nature of the system. And one possibility, block-nested loop join cannot do that, but one possibility is a single pipeline hash join, for example. One of the classic join algorithms, the basic idea is that for every hash join means you have a hash index on one of the relations, and one input relation is read from the intermediate results, right? And the other one is pipelined through the join operation. And So one of the tables, like the B table, has a hash index. And I know what is in there and what is not. So whenever I have something in the A table, I can look it up in the hash table whether this matches any of the things or whether this does not have a partner in B, right? In case it matches, I need to wait until the matching tuples are produced. In case it does not have a partner in B, I can throw it out immediately, right? Clear? Where the difference is? But I need this hash table, definitely. So the tuples of B have to be stored in a hash table. And the hash function is used on the join attribute. So all tuples showing the same value for the join attribute are in one bucket. Still, you might have false positives because there may be hash collisions, but we can deal with false positive when it occurs. Okay, so every incoming tuple via a pipeline is hashed by the join, and then we compare each tuple to the respective B bucket, and those that match can be returned, right? And those that do not match are thrown out. We don't need them anymore. Good. If we do that on both sides, we can do a double pipelined hash join. So we build a hash table for A and B, kind of memory intensive, but still. And whenever one of the tuples from either thing arrives, we look it up on the other side, produce the output, or throw it away if it does not have a partner on the other side, right? So both are producing, and we will just look up what happens on the other side. So if a new tuple from A arrives, we insert it into the A table, check the B table if there's a join partner, if then we return the matching tuples, and same thing on the other side. Good. So what happens here? For example, here we have this new tuple, right? B231 with the hash value and insert it into the hash table. Then we will take the hash value, make a lookup in the hash table of A, see, aha, there is already one, A3, so we need A3 B2 as an output tuple. Okay? So looking it up, this is this idea of cross-referencing by the hash table. Okay. In pipelines, we said the tuples, like the operations are sequentially applied directly to the tuples without storing it before or producing the whole result before. But now we have the problem in a distributed setting that the shipping of individual things may be kind of expensive, because think about TCP/IP networks, right? That might be between different processing units. TCP/IP units need headers, right? They need to package the information in packets, right? For sending them. If I take every individual tuple, build a packet out of it, have the packet received, acknowledged, and so on, right? That might not be the most effectual way of dealing with the things, right? We should batch more data together to get kind of the best possible communication costs. Because communicating on networks means we set up the communication channel, we compose the message with header and everything, right? The payload, if we just take single tuples, is amazingly small, right? Then we receive, we decode, we acknowledge, and finally close the channel, right? A lot of communication for a single tuple here, right? Bad idea, not a very good idea. What we rather do is tuple blocking. We do not send single tuples, but rather block containing multiple tuples, little batches, not producing the whole result and only sending that. But whenever a batch is ready, such that the payload of a packet is met, with the number of tuples that I have, then I send off a packet. Then I take the communication overhead, right? And then, of course, I have to iterate, adapt my pipeline iterators so they can cache the whole packets, right? And so on. Sometimes I don't do single individual packets, but even bigger batches, right? Because of course, for every single packet, I still have the open communication channel, acknowledgement, blah, 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 that for bigger batches I don't need. Good. Summary. So distributed query processing has a lot of constraints similar to centralized query processing, but we can exploit certain things, right? And we can compute cost factors that are basically comparable to what we have in classical query optimization. We have to focus on network costs, we have to focus on the model of the network, on things like shipping of data and query paths. We have to talk about fragmentation and allocation schemes to figure out whether things can actually produce results. And we might have different optimization goals, for example, the response time versus the total resource consumption, right? The throughput of the network. Very often in distributed settings, we rather care about response time, about quality of service, than about throughput, right? Highest throughput is not always necessary. User satisfaction is kind of the quality that we want to have, right? We talked about generic query reductions to do some first pruning. And of course, what we showed in this lecture was very basic techniques. I mean, you can do a lot more. We had the machine learning discussion in the middle, right? So there are a lot of algorithms that are more sophisticated, but they all work on the same principle, right? And that is something that you can read up. State of the art in distributed query processing is from 2000, and there you see the basic ideas contributed, right? And what can be done and how learning comes into the game and so on, right? So this is one of the things. Next time, we will talk about distributed transaction management and take it to the next level. Thank you.